For nearly 40 years, Uranus was the planet we thought we could ignore. Not because it was actually simple, but because it looked simple. A smooth cyan disk, a quiet, featureless giant. The boring planet. The one that didn't seem to have anything left to say. And then, Voyager 2 flew past in 1986, and the story locked in. Every giant planet we understand even a little bit has a basic signature. It leaks heat. Not sunlight, internal heat. Leftover energy from formation, slow gravitational settling, deep interior processes that keep the planet quietly glowing in infrared. Jupiter does it. Saturn does it. Neptune does it dramatically. But Uranus? Uranus looked like the exception. Like the furnace was off. The numbers from that flyby snapshot suggested something almost unsettling. Uranus appeared to be giving off barely any extra heat at all. Almost exactly what it absorbed from the sun. A giant planet in near-perfect balance. A thermal corpse. That single idea shaped decades of planetary science. It shaped the way we modeled ice giants. It shaped the way we guessed what countless exoplanets might be doing inside. And now, today, that story has taken a hit that it may not recover from. Because modern analyses, using far better infrared capabilities and far longer data sets than a fast flyby could ever provide, indicate that Uranus is not thermally dead. Uranus appears to be emitting more energy than it receives from the sun. Not double like Neptune, not by a dramatic factor, but enough to change the entire case. Roughly 12 to 15% more. 12 to 15%. Small enough to sound like trivia. Big enough to be a crisis. Because it means something very specific. The dead planet is leaking internal heat after all. It means the old conclusion wasn't a fact of nature. It was an interpretation built on a narrow window. And once you accept that, one question takes over everything. Where was that heat hiding? To understand why this matters, you have to see what scientists mean by a planet's energy budget. It's not mystical, it's accounting. Energy in, energy out. Sunlight hits Uranus. Some is reflected away. The rest is absorbed. Absorbed sunlight warms the planet. The planet radiates heat back into space, mostly in infrared. If Uranus radiates exactly what it absorbs, then internal heat is essentially zero. If Uranus radiates more than it absorbs, then something inside is contributing energy. And here's the part that always made Uranus so strange. Uranus sits about 1.8 billion miles from the sun. The sunlight out there is weak. If any giant planet was going to need internal heat to stay alive, it should be Uranus. Yet for decades, it looked like the planet was running on almost nothing. Meanwhile, Neptune, about 1 billion miles farther out into colder darkness, radiates more than twice the energy it receives from sunlight. So we had two ice giants that should have been cousins, and they behaved like opposites. Neptune, a glowing engine. Uranus, a silent shell. That gap begged for an explanation, and scientists gave it one. The most famous is the giant impact hypothesis. The idea is brutally cinematic. Early in solar system history, something roughly Earth-sized, maybe bigger, slammed into Uranus, knocked it onto its side, and in the process, vented its internal heat into space. A catastrophic reset. That story had everything. A reason for Uranus's extreme tilt, and a reason for its missing heat. It was neat, it was clean, it fit the data. But fit the data depends on what data you have. Voyager 2 gave us a flyby, a snapshot, a short look at one season, one geometry, one moment in a planet's long, slow life. If you build 40 years of certainty on a snapshot, you are taking a risk you don't fully feel until the snapshot breaks. So what did the newer analyses do differently? They stopped treating Uranus like a single photograph. They measured thermal emission over time. They used modern sensitivity. They looked at the planet as a whole disk, not just a passing slice. And the planet no longer looks like a corpse. It looks like something with a pulse, a faint one, but real. So again, where was that heat hiding? There are a few serious possibilities, and none of them are comfortable. The first possibility is almost embarrassingly simple. Voyager caught Uranus at a weird time. Uranus has extreme seasons. Its axis is tilted by about 98 degrees. That means for long stretches, one hemisphere gets prolonged sunlight while the other is in darkness, and the geometry changes dramatically over its long year. If the atmosphere and upper layers respond differently at different seasons, the planet's outgoing infrared could vary in ways a single flyby would never capture. This would mean Uranus didn't change today. We just stopped pretending one moment was the whole truth. But there's a second possibility that's far more interesting and far more disturbing. Uranus may have internal heat, and it may have had it all along. But the heat might not be able to escape, because heat escape isn't just about having energy, it's about transport. On many planets, heat moves upward through convection. Hot material rises, cool material sinks. It's a slow churn, like a lava lamp, and it is incredibly effective at moving energy. That's how a giant planet can glow in infrared for billions of years. But convection can be suppressed. If the interior is layered, strongly stratified by composition and density, you can build a stable structure where layers don't mix easily. And if they don't mix, heat transport slows down. The heat doesn't disappear, it gets trapped. Imagine a furnace running in a basement, but the ceiling is built from thick insulation. The furnace is real, the energy is real, but upstairs you might feel almost nothing until the system changes. In Uranus, those layers could be made of different mixtures of water, ammonia, methane, and other volatiles under extreme pressure. Not ice like a freezer, but hot, dense fluids that behave nothing like anything on Earth. If Uranus is stratified like that, then the planet isn't dead, it's muffled. And that turns the giant impact story upside down. Instead of the impact blew the heat out, the impact might have created the layers that keep heat in. Not venting, insulating. A collision that didn't kill the engine, but wrapped it. And if that's true, it doesn't just explain why Uranus looks quiet. It explains why Uranus could fool us for decades. Because the planet would be hiding its most important physics beneath a calm surface. Now there's a third possibility, and it's the one that feels like it shouldn't happen. Except it can. Uranus may cool in episodes. Planetary cooling doesn't have to be smooth. If transport mechanisms switch modes, if layering changes, if convection turns on and off, if deep phase transitions open and close pathways, then heat output could vary over long timescales. Voyager might have seen Uranus during a quieter phase, and we might now be seeing a slightly more leaky phase. Not dramatic, not a sudden awakening, just a planet whose internal weather is not steady, not polite, not linear. And then there's the part that sounds like science fiction, except it isn't. Deep inside Uranus, the materials are under pressures so extreme that familiar substances enter unfamiliar phases. One candidate phase discussed for ice giants is superionic water, a state where oxygen atoms form a rigid lattice while hydrogen ions move through it, making the material highly electrically conductive. That matters because conductivity affects magnetic fields, and Uranus has one of the strangest magnetic fields in the solar system: tilted, offset, lopsided. If parts of Uranus's interior are dominated by exotic conductive phases, it could help explain why both the magnetic field and the heat transport behave in ways that don't match our neat expectations. Important: this is not confirmed by direct sampling. It's model-driven, supported by laboratory physics at extreme conditions, but still not directly measured inside Uranus. Which is exactly why this energy result is so dangerous. Because it pushes the interior back into the category of, we don't actually know. And the implications are bigger than Uranus. Because if you zoom out to exoplanets, the most common planet size we've found is not Earth-sized and not Jupiter-sized. It's in the neighborhood of Uranus and Neptune, sub-Neptunes, ice giant scale worlds, the kind of planets that dominate planetary census charts. If we don't understand how heat moves inside Uranus, then we don't understand how the most common kinds of planets in the galaxy evolve. We don't understand how long they stay warm, how their atmospheres change, how their internal structure locks in, how their magnetic fields behave, how their radii shrink with age. We've been using Uranus as a reference point, and now that reference point is unstable. So what would settle this? Not a better argument, not a new simulation, a measurement, a probe. Because right now, we are still living in the shadow of a flyby. To actually answer the "where is the heat hiding" question, you'd want to drop a probe into Uranus's atmosphere and measure temperature and composition as you descend. You'd want long-term orbital mapping of infrared emission across seasons. You'd want gravity field data that tells you how mass is arranged inside. You'd want magnetic field mapping that reveals what kind of conductive layers might exist below. And then you'd be able to test the big fork in the road. Is Uranus insulated, or is Uranus episodic? Because those are not the same story. They point to different interiors, different histories, different physics. And here's what makes Uranus unsettling in a way that doesn't show up in pretty pictures. For decades, we treated quiet as simple. But quiet can also mean blocked. Featureless can also mean we're staring at the wrong layer. And now we have a planet that may have been mischaracterized for nearly 40 years. Not because anyone was careless, but because the evidence was thin and the snapshot looked convincing. So if you strip everything down, the mystery becomes almost uncomfortable in its simplicity. Uranus was labeled a thermal corpse, and now it's leaking extra heat. Not enough to make it Neptune, enough to make it a problem. And we still don't know which explanation is true. Seasonal misread, layered insulation, episodic cooling, exotic interior phases, or some combination that no one has fully nailed down yet. Which is why Uranus might be the most dangerous, boring planet in the solar system. Because it forces a question that echoes far beyond our neighborhood. If a giant planet can hide something this fundamental in plain sight, how many other settled stories in planetary science are built on snapshots that haven't met their replacement yet? And what happens when we finally go back? Not for hours, but for years. And Uranus gives us the one measurement that makes only one of these explanations survive. What would that measurement look like? And if we saw it, which of our assumptions would it destroy first? Veil origins, impossible truths.